Thank you very much for attending this session. My name is Vidyasagar and I'm a senior scientist at Beyond Limits. Today I'll be presenting to you about GPU-accelerated deep reinforcement learning for the application of field planning in the energy industry. I will begin by touching upon and contextualizing field planning by explaining subsurface reservoir simulations and the sequential decision-making problem of well placement, trajectory, and control optimization. Next, I will give a short introduction to deep reinforcement learning to those who may be new to the subject, and I will also follow this up with a short explanation of our soft actor critic or SAC framework. After that, I will touch upon algorithmic implementation, which ties in with the computational resource requirements for our application. At this point, I will explain some of the intricacies and fundamental issues that one encounters when coupling deep reinforcement learning to reservoir simulations or PD solutions in general. Once this is done, I will highlight our benchmarking results on A100 GPUs together with a short discussion. Finally, the talk is concluded by highlighting extensions and future application of the approaches that we present in this talk. Let us begin by understanding the concept of field planning. In the upstream energy industry, one of the key aspects is the exploration phase, which consists of energy companies locating and appraising the preservation of hydrocarbons that are contained within discovered fields. During this phase, seismic surveys, together with geostatistical analyses, are used to map the different regions and obtain reservoir properties. Once this is done, multiphase porous media flow or reservoir simulations are performed to understand the mechanisms of fluid transfer and the pressure distribution within the reservoirs. Wells, which are used for production to extract hydrocarbons or injection to increase pressure and encourage the flow of hydrocarbons, are modeled as line sources and sinks within the reservoir simulations, forming an algebraic constraint sets that couples to the original PDEs. Now, these are a critical modeling aspect when it comes to reservoir simulations. Maximizing the efficiency and the amount of extraction with minimum drilling impact requires careful consideration of well drilling plans. Now, the whole idea behind field planning is to determine the locations, trajectories, and control of these wells in an optimal manner. Within the context of our discussion today, we will focus on the optimization of well placement and trajectories that couple specifically with the porous media flow simulations. Now, this problem can be described as a sequential decision-making process with a spatio-temporal nature, essentially answering the question of where and when to drill wells of specified trajectories in order for us to really maximize the efficiencies. If we looked at the topology of the search space for this optimization problem, we immediately see that there is a combinatorial explosion even for very small model problems. To give an example, for a reservoir model that is refined to a grid consisting of only 20,000 cells, within just 5 sequential steps, each of which consists of choosing a well location, there are in excess of 10 to the 14 possible combinations. Now, a canonical analogy for this could be the game of chess, which deep reinforcement learning has shown strong success at, and this consists of 5 million or 10 to the 6 combinations after just 5 moves. Of course, this in reality, reservoirs could consist of hundreds of millions of cells, with thousands of wells corresponding to sequential decision-making steps, which really highlights the need for intelligent algorithms and careful design. Getting into the specifics of the optimization problem, our goal is simply to maximize the net present value or NPV, which is an indication of the total dollar value associated with production. This is a non-deterministic polynomial time or NP-hard problem, which has seen attempts in the past using brute force search, gradient-based methods, particle swarm optimization, and genetic algorithms. In our work, we choose an alternative strategy, which is deep reinforcement learning, or what we abbreviate as DRL. Over the past few years, a few reservoir model candidates have emerged as test beds for benchmarking NPV optimization for well trajectories. These include the Olympus model, SAI-GUP, and the EGG model, And it is the last of these that we choose to focus on for our application and the benchmarking that will be presented later in this talk. Now, this model was first presented by Janssen et al. In the Geosciences Data Journal in 2014. The reason why they chose this model are very simple. It consists of only 20,000 cells, and this makes the simulation times reasonably tractable. Additionally, because of this simplistic geometry which you can see on this screen, the solutions provide mathematical intuition and conform to easy interpretation. For instance, the placement of an injector well on one corner of the reservoir and production wells on opposite corners as an example of a possible strategy. Finally, the insights that we gain from this model are really anticipated to extend in a straightforward manner to much more complex reservoir models, and I will touch upon these in the later slides. I would like to now switch focus with an introduction and a background to our deep learning framework. But first, I would like to begin with a short introduction to DRL itself. Now, deep reinforcement learning is an emerging field, and this has empowered breakthroughs in a number of different industries, including the games of Go and chess, and also in the biomedical industry with figuring out different methods of protein folding. Now, reinforcement learning itself is a method of dynamic programming, whereby a global optimization problem is sequentially decomposed into recurrent subproblems. Now, the important point is that these subproblems are much easier to solve than the original global problem itself. Mathematically, in our context, we solve in tandem recurrent Bellman equations, which dynamically express future states as pure functions of current states, and this works well for Markov decision processes. And of course, this is something that I will also touch upon in the later slides. In solving these equations, we use convolutional neural networks as surrogates for estimating the actions and the values that result from these actions. Now, while our specific problem of well placement is temporally discrete with finite time steps, the same ideas can be used for a discrete to temporal continuum problem, which is continuous in time. And this leads to the Hamilton-Jacobi-Bellman equations, which are a set of PDEs. Now let us take a closer heuristic look at deep reinforcement learning. While there are many different flavors of deep reinforcement learning, the concepts that unify them are fundamental. AI or RL agents, which denote a cluster of algorithms which may consist of multiple neural network approximations embedded within Bellman equations, perform different actions and predict different actions based on the states. Now, these actions trigger changes in the environment, and this environment itself can be a simulation or it may be a real measurement in a real physical system. The environment then returns a reward together with an altered state back to the RL agents, which are used to train the different neural networks and improve the prediction of actions. In our application, the environment consists of a multiphase porous media flow or reservoir simulation environment. Within the same context, the actions involve the locations and the trajectories of the wells. The states consist of pressures, fluid saturations, and other primary variables, and finally the rewards consist of either the NPVs or modifications thereof, specifically NPVs that are normalized by well trajectory lengths in order to avoid impractical solutions and excessively long trajectories. Now, in summary, there is a coupling between a simulation environment and an RL agent, which has within it embedded different neural network approximators. Now I will quickly glance through some definitions and concepts that are central to the reinforcement learning framework. First, we have the value, which is an expectation of the reward given a particular state, and this is expressed here mathematically. More pertinent to our discussion is the action value, or what is known as the Q function, which returns an expectation of the reward given a state-action pair of functions, here denoted as S0 and A0. Now these are the building blocks of the Bellman equations for the finite sequence, finite horizon problem. An interesting point of note here is that non-unique actions may describe the same optimal policy, and this means that there is a surjective nature to this problem, which adds complexity to finding optimal solutions. We use a specific flavor of deep reinforcement learning methods that are known as soft actor critic methods. Now, there are several advantages here, and these are the reasons why we choose to use the SAC method. Firstly, it is a model-free method, and we do not embed any information about the reservoir field planning within the DRL algorithms. And for our use, it provides direct extensibility for different use cases, including different reservoir models. A distinguishing feature of SAC methods is inherent stochasticity, and we have adapted some aspects including entropy regularization, which I will talk about briefly. This helps us overcome regions of flat topology in the objective function landscape. To give an intuitive understanding, you can imagine that within a reservoir there are certain regions whereby placing wells within a specified radius may or with a different curvature may not increase or decrease the NPV. And the stochastic forcing really helps us to avoid being stuck in these regions and find more optimal solutions. Finally, the SAC method itself uses a very conservative estimate for the action value approximation. And in the original SAC algorithm, it takes the minimum of 2 concurrent Q estimates. We have made certain modifications of this within our own proprietary framework. Now, the graphic in the bottom of this slide, it highlights the important elements of the framework, and I will just briefly touch upon this. Firstly, we ingest the policy parameters, initial Q targets, and set up an empty replay buffer which contains the memory of different simulations which can then be used to train the networks. Now, the first step within the environment step iteration is to perform an action with a certain set of perturbations. We then observe the new states and calculate the rewards that are associated with these states. Now, if the action is permissible and an update is performed, then we go through a sequence of calculations which are then highlighted in blue in this slide. Due to the importance of this particular state update, I'm just going to touch upon this very briefly with a mathematical formalism. Now, the first step in this update is the updating of Critic neural networks based on the MSBE loss function, which is also the mean square Bellman error. Once this is done, the actor neural network is subsequently updated using the more conservative of the Q estimates and using the Kullback-Leibler divergence. Now, the next step is the entropy regularization, which determines the nature of the noise or the temperature within the system. And finally, once this is done, the Q targets are updated using a linear parameter, and the purpose of this interpolation is to stabilize the update with some phase lag or damping to ensure that the new targets do not cause strong oscillatory behavior when it comes to the targets. I want to now take a step back from the mathematical formalism to highlight one of the main advantages of using this SAC DRL framework, which is known as transfer learning. Now, above and beyond solving the main optimization problem, the outputs of the framework also includes trained weights for the actor and critic neural networks. Now, let's just focus on the actor neural network here. This predicts our actions, or in our case, well locations and trajectories, given the corresponding states, which are in our case pressures and fluid saturations. Inference is performed on these networks, and this can be used independently and separately from the main framework in order for us to understand the fundamental physics of the system. Specifically, there are three main directions that we are experimenting with in terms of transfer learning. Firstly, training on a coarse reservoir grid and understanding how this may accelerate training on a finer grid, given the fact that we may add a few additional layers on top of the network that is trained on the coarse grid. Secondly, an idea is to train on simpler physics, for instance, in our reservoir case, using 2 or 3 phase systems, and then extrapolating this to a multi-phase, multi-component system. Finally, we are also experimenting on going from simple model geometries to very complex geometries as shown in bullet point D that may incorporate more complicated physical equations. Now let's take a look at the computational resource requirements as well as a high-level overview of the algorithmic implementation. In this graphic, we have an overview of our field planning agents from a very high vantage point. We have our reservoir data, and this consists of the mesh, the porosity, the permeability, and other static information, and this is used to initialize the simulations. We also have the initial and boundary conditions for the simulations. These are fed together with the parameters for our reinforcement learning, which may include the time span or lifetime of the reservoir, the number of wells to drill, the time discretization, and finally the reinforcement learning configuration and heuristics. Once this is ingested into the deep reinforcement learning framework, a replay memory buffer is set up by running n number of simulations by different virtual workers interacting with the simulation environment. This initialization setup consists of n random searches to start the training of this 3D convolution neural network, which is our action predictor or actor that takes the states and predicts the well locations. Together with this is our value estimator or critic that takes the actions and the states and predicts the value of these towards achieving our target. Once the initial training is over, the inference of actions from the actor begins the reinforcement learning cycle with some stochastic perturbations that ensure that we have a spread of results. These are then passed on to n parallel workers which perform simultaneous simulations and return the altered states together with the rewards or NPVs back for training both the actor and the critic neural networks. I will now switch focus to more of a theoretical discussion on some of the fundamental issues that arise if we were to naively consider our reservoir well optimization as a black box problem without a full and complete understanding. I will also highlight some of the resolutions that we've come up to solve these issues in the coming slides. Now, one of the fundamental assumptions that we make when decomposing a problem into its recurrent form is the Markovian property of the system. In very simple terms, the probability of reaching a future state for a Markovian system depends only on the current state and not the past history. As a corollary, the system should evolve in a path or history-independent manner. For a Markov decision process or MDP, all the possible information that is used to describe the state is contained within the state variables. Classic reinforcement learning algorithms are designed specifically for MDPs, and the big question here is that, are there situations in our example where this assumption breaks down, and what are the resolutions in such specific cases? To answer this question, we first have to take a long step back to consider a very canonical analogy with an inverse pendulum problem, which I will refer to several times in the coming slides for its simplicity. On the left here, we have a blue pendulum, and on the right we have a red pendulum, and both of these pendulums start off initially off-center. The blue pendulum has an arm of fixed length, and we apply a torque tau to perturb the system. For the red pendulum, we do something that's a bit more interesting, that is, to try and perturb the system by changing the length of the arm. Now, in both cases, the governing physics are identical, and the states are described by the angle theta and the angular velocity theta dot. However, the way that the actions trigger changes in the environment are very different, and in the system on the right, we have two important complications that make the system violate the Markovian assumption by making it a partially observed Markov process. Firstly, our state observation on the system on the right is incomplete without taking into account the length L as a function of time. So the new state should incorporate theta, theta dot, and L. Secondly, our actions operate directly on this L, which has become a part of the state variables. So we need to keep track of our previous actions in order to understand the evolution of the length. Due to both of these factors, every time an action is performed, the governing equation of the environment itself changes, which needs to be taken into account. Now, this is a very trivial case whereby we can get around these problems easily, but as we consider our more complex reservoir examples, there are many intricacies that would normally be overlooked if we simply took it as a black box RL problem without understanding its intricacies. Let us in fact consider this in more depth to understand how this simple analogy with the red pendulum extends this case. Our reservoir simulations are governed by partial differential equations, PDEs, as such as shown here on this slide. And this consists of the oil, water, and gas systems respectively acting together over a domain for a given set of initial and boundary conditions. These equations are then coupled to the algebraic constraint set that solves for the flow within the wells and how it drains fluids from the reservoir. Morally, you may consider these as part of the boundary conditions, partial omega, that dictate the evolution of the PDE solution. Of course, this means that every time an action occurs, that is, the placement of a well, the system itself changes in analogy to the red pendulum, and one must keep track of these changes over the lifetime of the reservoir. Formally, the observable state consisting of saturations and pressures is insufficient to describe the system, and the feedback from the action memory is needed to augment this state when training the actor and the critic neural networks. Now, while the previous slide highlighted a case of actions changing the system dynamics itself, in addition to the state, the situation of partial observability arises due to more fundamental reasons in our case. In many physical systems that occur in nature, the concept of scale separation exists. For example, in our case, there is pore scale flow and granular mechanics that drive the continuum description of large reservoirs. As shown in the graphic on the bottom of the page, what we are trying to model is reservoirs on the scale of tens of kilometers, while the flow itself occurs at the centimeter scale and the fluid mechanics happens at the microscale. And the influence of these low-scale mechanisms cannot be ignored at the macroscale continuum, and interestingly, sometimes it introduces the concept of history dependence. As an example, specifically in our reservoir case, hysteresis occurs in the relative permeability and the capillary pressure of the interaction between the fluid and the porous rock in which it is flowing through. Now, the microscopic origins of this effect is due to surface tension when two liquids are impinging on a solid surface. Classically, this is modeled at the continuum level by keeping track of the historical maximum saturation, which is an indication of the angle, that the contact angle or the wetting angle by both of these fluid phases. Now, what do we do in our situation? This historical maximum saturation becomes an internal variable that exists during the lifetime of the reservoir, but something that we cannot directly observe at the continuum level. Of course, this introduces a history dependence which directly violates the Markovian assumption, but in our case, this can be overcome quite simply by taking into account the historical maximum as an augmentation to the original state vector. And this, of course, completes the system and ensures that it becomes an MDP. Another very interesting complication is the temporal aspect of the learning problem. What we have here is a finite time horizon problem. That is to say, we want to maximize the production value within a very small fixed time frame. This complicates the optimization process in several ways. Firstly, our rewards and NPV metrics are cumulative in time as opposed to canonical cases. Additionally, a policy that is based on incremental maximization of rewards at given intermediate states and the accumulation of this set of rewards is not at all equivalent to one that does maximization over the entire lifetime. As an example, you can see the red line on the plot on the bottom right, which would result if incremental maximization is used, due to constraints existing on the number of wells and the lifetime of the reservoir. We get around this through several means, one of which is to bias solutions through temporal delay with a gamma decay parameter that enables solutions such as the green line, which has a slower initial slope but then a higher overall NPV within the lifetime of the reservoir. Now I will shift focus to our computational benchmarks using the newest generation of A100 GPUs. In order to quantify the metrics of using A100 GPUs over 20 and 96 logical CPU processors, we have performed detailed benchmarking for both intra and inter-operation performance. There are several main points to consider when it comes to performance benchmarking comparisons. Firstly, we judge value through the best solution that is found in terms of raw NPV, Specifically, when we talk about vertical wells of equal length, it is just directly the NPV, or the normalized NPV when we start talking about curved wells and trajectories. Secondly, the distribution of the NPVs indicates the convergence and the power of the method. Finally, we should consider the time taken to reach a fixed number of episodes as well as the derivative of this, which gives us the instantaneous speeds throughout the learning process. For this purpose, we run a series of RL calculations with a fixed time of 120,000 seconds using 20 CPU logical CPU cores, 96 logical CPU cores, and compare it with A100 hybrid runs. While we are doing this, we observe the number of actions that are inferred at the end of the time period. We figure out the speed indicative of the peak performance during this time. And finally, we obtain the best normalized NPV at the end of the calculation, and this is used for the comparison. We can now take a look at some of the qualitative results for the egg model that I had mentioned at the beginning of the talk. Here, the model is rendered as the mesh in orange. The oil-saturated regions within this mesh are illustrated as black boxes, and the trajectories of wells are also rendered as these metallic lines. Now the goal here is quite simple: to design these trajectories in order to maximize the production value. I will now run through the first benchmarking example that is done with vertical wells only, and this code is a hybrid run using 90 logical CPU processors and A100 GPUs. Running over the course of 36 hours, the learning framework reached a total of almost 166,000 actions that are inferred to reach a peak NPV of approximately 51 million. We can see the results of this calculation depicted on this graph. There is first an initialization phase where the RL agent oscillates around an intermediate value. After approximately 50,000 explorations, it begins a convergent phase around 40 million, which then steadily grows to reach a peak NPV. We can immediately note that there is inherent stochasticity in the method, whereupon reaching 40 to 50 million NPV, the solutions keep oscillating due to the temperature-induced noise. Now, this is a characteristic of the soft factor Critic method that prevents the method from being prematurely stuck in local optima. And of course, the decay of the noise can be tuned heuristically and also follows from entropy regularization parameters. Now, it is also interesting to note that there are occasionally negative NPV solutions that are found by the code, and these correspond to situations whereby the cost of injection outweighs production, which of course is the sort of situation that we want to avoid. Now we can run through some of the results of the benchmarking, in particular the normalized speed of learning as shown in the chart here. The learning itself becomes slower in time because the amount of training data increases with time as we generate more and more simulation results. We can see in red the speed of the code using A100s, and over the entire course of learning there is a significant improvement over the blue curve, which shows the results using 96 logical CPU processors. Now the x-axis refers to the number of actions inferred, and ideally we want to explore at least 50,000 actions to ensure convergence of the NPV. When we quantify and tabulate all of these results, in terms of all the key metrics, A100 GPUs significantly outperform 96 logical CPU processors. In terms of the time elapsed to reach a fixed number of action explorations, we have a 245% improvement over 20 logical processors and 153% improvement over 96 logical CPU processors. In terms of the speed, which is really just the derivative of the time elapsed against the number of actions, we have an almost 148% improvement in the mean or average speed and 184% improvement in the peak when comparing A100 results to 96 CPU processors. Similarly, we have large improvements comparing A100s to 20 cores, including an 11x speedup for the peak speed. In terms of the optimization value, or NPV, there is an 8% improvement over A100s over the 96 logical processors and 35% over 20 logical CPU processors. Now, we really need to emphasize here that every percentage point is important when considering the NPV, because in the real world this corresponds to millions of dollars in added value. Additionally, as we approach the extraction limit of the reservoir, theoretically it gets exponentially more difficult to find solutions which improve just a single percentage point. So it has to be emphasized that this is actually a very significant result. It is also important to note that our best A100 solution significantly reduces the drilling length over the CPU runs. I will now talk about some of the key computational improvements that we are working on, together with extensions and future applications of the DRL framework that I've presented today. In terms of the improvements that we are currently working on, we are looking at optimizing the various aspects of our DRL framework to use GPUs more efficiently. We are also trying to overcome a parallelization bottleneck that is caused by the simulation environment, and this at the moment limits the computational efficiency of our code through Amdahl's law. Our priority is to overcome this and improve the simulation speed to match the learning process. Now there are two important aspects here that I have to describe. Now the first of this is that we have to couple our reinforcement learning to a full GPU simulator, and this will ensure that the simulations are not only fast, but maximize the GPU resources. Secondly, we're working to ensure that the simulation concurrency is high and there are no synchronization overheads, which can cause a large slowdown in the code. We are also actively working on individual aspects of algorithmic improvements. This includes intelligent subsampling of the replay memory for the learning process of both the actor and the critic neural networks. Additionally, we're looking at incorporating model order reduction for the environment, as well as the predictions that are based on partial states, playing with the idea of POMDPs. Another very interesting area for us is adaptable neural network architectures for the actor and critic networks, which is actually very important in our case. As you can imagine, for our application, a very simple reservoir model could be approximated with 5 or 6 hidden layers and just a few thousand weights. However, for a very complex reservoir model, this may need up to 100 million weight parameters. It would be very helpful for us if these could be auto-tuned. Additionally, embedding phase lag within these neural networks through recurrent neural networks or LSTMs could be a method of solving some of the POMDP issues that I had highlighted earlier in the talk. Finally, something that we are looking to do is reduce the data transfer bottlenecks by working on binary serialization and other techniques. To conclude, we have shown that deep reinforcement learning is a very promising tool for solving complex industrial problems. We strongly believe that using these tools will enable tangible breakthroughs in the energy industry. Specifically, as we have shown, DRL is a prime candidate for HPC in the upstream energy industry, and this is in alignment with the AI and digital transformation strategies that many companies are adopting today. In this presentation, I had talked about our DRL methodology used to solve well placement optimization for field planning and the innovations that are needed to make it work for our specific case. However, we do not stop here. Currently, we're looking into using the same techniques to do in essence the reverse of petroleum extraction through carbon capture and geological sequestration. With clean energy efforts gaining strong momentum in recent years, this subject has attracted a lot of interest in the energy industry. It is quickly becoming a prime driver towards offsetting carbon emissions. In this case, instead of extracting hydrocarbons from reservoirs, we try to pump carbon dioxide into depleted reservoirs and saline aquifers. This works hand in hand with big data analysis that can be used to identify safe storage sites for carbon sequestration. Overall, we believe that there are many opportunities to extend deep reinforcement learning to other industries, from power optimization to wind farm control to plant operations and so on. We sincerely hope that these applications will enable us to achieve new breakthroughs in unexpected ways. And on this optimistic outlook, I thank you very much for your attention. Thank you very much.